How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at vapor pressure. So our objectives will be to explain vapor pressure on a molecular level and how it relates to a substance boiling point, as well as interpret charts for vapor pressure versus temperature. We need to be able to determine which has a stronger intermolecular attractive force, as well as determine the boiling points under certain pressures. So vapor pressure. So even below the boiling point, some liquid will vaporize into the gas phase. So if you take a look at this animation courtesy of FET.colorado.edu, we got a liquid phase, and some of those molecules end up in the gas phase. And if we come back after a certain amount of time, you can see more of them have vaporized. So the vapor particles will also condense back into the liquid phase. Once we've reached this equilibrium, we call it a dynamic equilibrium. So a dynamic equilibrium is when two opposing processes occur simultaneously at the same time at equal rates. So for this dynamic equilibrium, we have the rate of liquid going into the gas phase is going to end up equaling the rate of the gas phase to the liquid phase. So we end up with overall no change, but things are still actually changing, right? We still have liquid going to gas going to liquid, but the amounts stay constant over time. So the pressure exerted by these gas particles when we're at equilibrium is called the vapor pressure, right? We got this vapor, it's a gas, it's exerting a pressure, boom, vapor pressure. So at any given temperature, some particles will have enough kinetic energy to evaporate. So here we have like a chart showing the fraction of molecules and their speed or their kinetic energy. Let's say that right at this temperature, that's what you need to vaporize. Well, right now, all of these particles are able to evaporate. At higher temperatures, more molecules will have enough energy, which will increase the vapor pressure. So what would this curve look like at a higher temperature? Well, we're going to have more things at a higher temperature, which means now, hey, instead of just this much being able to vaporize, all of these particles can vaporize. We're going to have more vapor. We're going to have a higher vapor pressure. So as temperature increases, vapor pressure increases. So there's this handy dandy chart that will show you some substances and how their vapor pressures change over time. This is courtesy of like the New York State chemistry reference tables. We're going to refer to this, but it has 4 different substances and it shows how their vapor pressure changes over time or temperature. So volatility, volatile, vocab word, means readily evaporates. So substances with high vapor pressures are more volatile than those that have low vapor pressures. Basically, as we increase temperature, we increase the vapor pressure, and because we have an increase in volatility, right? So we have vapor pressure over here, temperature on the bottom. So as we increase temperature, the vapor pressure increases for all of these things. So put these gases in order of increasing volatility. Well, let's just pick a temperature and see which one has the most vapor pressure. So the lowest vapor pressure is going to be ethanoic acid. That's going to be my lowest. And then water is going to be my second lowest. Ethanol, third lowest. And propanone is going to be the most volatile. So propanone is the most volatile because it's got the highest vapor pressure at any given temperature. So if we take a look at one temperature, we go, hey, propanone, highest vapor pressure, it's the most volatile out of those 4. Intermolecular attractive forces dictate how volatile a substance is. So which substance do you think has the strongest intermolecular attractive forces? Well, again, let's just picture temperature, pick one, and we could probably rule out those middle ones. So it's really going to be, hey, if I'm asking for an extreme, let me look at the 2 extremes. I got ethanoic acid or propanone. And think about it. As attractive force increases, the volatility and vapor pressure should decrease, right? The more strongly they are attracted together, the less likely they are to evaporate. So which one of these is going to be the strongest attractive forces? It's going to be ethanoic acid, right? And if we take a look at the particle diagrams, the more that these liquid particles are attracted to each other, the less likely they're going to vaporize. And you can even see some of these as they escape get kind of pulled back down because the attraction there is so strong. So vapor pressure and boiling point. So we know vaporization is when we have a liquid going into the gas phase. And this can happen at any temperature because some of the particles have enough energy to go into the gas phase. Things evaporate. This happens at the surface. So it's the surface molecules that are going to be able to actually go into the gas phase. Now boiling is when liquid particles on the interior have enough kinetic energy to break free of the liquid phase. So it's not just at the surface, it's on the interior of that as well. And this happens when vapor pressure is equal to the external pressure. So our boiling point is the temperature at which the vapor pressure equals the external pressure. So if we're talking about like our normal pressure, that's where we get the vocab term normal boiling point. It's a boiling point at a standard pressure of 1 atmosphere. So what is the normal boiling point for these substances? Well, we know 1 atmosphere is roughly 101.3 kilopascal. So we really just go over, hey, all right, at this pressure, propanone has that very same vapor pressure at what looks to be like, I think that's 55 Celsius. So at 55 degrees Celsius, propanone will boil because its vapor pressure is equal to the external vapor pressure. So if I do the same process for ethanol, it's almost right on there. So that looks to be at about 80 degrees. So roughly 80 degrees would be the boiling point for ethanol. If I look at water and follow it down, it's at 100 degrees Celsius. And for ethanoic acid, it looks to be in between, let's see, 115 and 120. So I'm going to call that 117 degrees Celsius. All right, so what would the boiling point of water be at an external pressure of 200 kilopascal? So we've almost doubled our pressure. What's going to happen to the boiling point? Well, we'd expect it to go up. If we have a higher pressure, things are going to get hotter, need to get hotter in order for vapor pressure to get up that high. And if we follow the 200 kilopascals over to water and then follow that down, that's at roughly 117 degrees Celsius. So that would be the boiling point at that temperature. And what's really kind of cool is pressure cookers. How do they work? All right, so when we have a substance that reaches its boiling point, it can't get any hotter without vaporizing, right? If we go back to the heating curves, when we're vaporizing things, the temperature is flat. If you add more heat to the boiling pot, it just means more water evaporates, but the temperature doesn't get any hotter. It stays at 100 degrees Celsius for water. Pressure cookers, they're basically pots that make an airtight seal, right? So here I have my pressure cooker and it's airtight. It means no vapor is going to be able to get out. So as we heat things up, the pressure inside is going to increase because some of that water vapor or some of the water is going to evaporate. The gas in there is also getting hotter. It's sealed, so the pressure is going to go up. As the pressure increases, so does the boiling point, right? So if we're going back to this, water went from 100 degrees Celsius to, if we doubled the pressure, 117 degrees Celsius. And that means if we can get higher temperatures, things will cook faster. That's one of the great things about pressure cookers is they'll cook things quicker because they can get hotter. And the opposite is also kind of problematic. If you live somewhere at a very high altitude, you have a lower pressure and your cooking temperatures are going to be lower. Things aren't going to get as hot. Water won't boil at 100, it'll boil at 90 something. So that means you're going to have to cook things longer, which I found very interesting. All right, summarize. Can you explain vapor pressure on a molecular level and how it relates to a substance boiling point? And can you interpret charts for vapor pressure versus temperature? I hope so. Hope you found it helpful. I'll see you in class. Goodbye.